Hi, welcome to Chemistry with Caroline. I'm a chemistry professor at a small undergraduate institution. I have 13 years of experience teaching organic chemistry, and today I want to share with you 5 concepts that are fundamental to mastering organic chemistry. So first we want to hone in on exactly what we are going to be looking at. Organic chemistry is the study of carbon-based molecules, and so we're actually focusing on a pretty small portion of the periodic table. All the molecules that we'll look at in this class are carbon-based and will have hydrogens on them. And then these atoms right here are commonly found on organic molecules, and we call those heteroatoms. So the first concept that we want to master is formal charge. Being able to assign a formal charge to an atom is important for predicting its reactivity, and 3/4 of organic chemistry is predicting the reactivity of molecules. So for an in-depth treatment on formal charge, you can look at my How to Calculate Formal Charge for Atoms Important in Organic Chemistry video. It should be queued up for you at the end of this video. You can also find it on my channel, Chemistry with Caroline. Here we're just going to look at one example of an atom that is commonly found in organic molecules and how we can recognize that formal charge. So we're going to look at oxygen, which is commonly found. I'm just going to draw a line. It's attached to something, but we'll look at the different ways in which we commonly see oxygen atoms. So we might see an oxygen atom that has 1 bond and 3 lone pairs of electrons. We might see an oxygen atom that has 2 bonds and 2 lone pairs of electrons, and that can be in different iterations. So it might be an oxygen atom that has a double bond and then 2 lone pairs, or maybe 2 single bonds. Okay, so I'm going to write an or in between here. Or we might see an oxygen atom that has 3 bonds and only 1 lone pair of electrons. And so that could also happen if it was a double bond and 1 single bond. So oxygen atoms have a valence of 6 electrons. That's the number of valence electrons that they have. So any oxygen atom that has 2 lone pairs and 2 bonds is going to be neutral. So these molecules in the middle, these atoms in the middle, are going to be neutral. Now this oxygen atom on the left here has 3 lone pairs. It has extra electrons. It's going to be a negatively charged oxygen atom, and we call those oxides. And if you have an oxygen atom on the right over here that has 3 bonds and only 1 lone pair, those are positively charged oxygen atoms, and those are sometimes called oxonium ions. So this is an example of a formal charge for an atom commonly found in organic chemistry, and you want to be able to do this quickly, okay? Because if an oxygen is negative, it's going to behave a particular way. If an oxygen atom is positive, it's going to behave a different way. And if it's neutral, it will behave yet another way. So you need to be able to assign these formal charges to predict the reactivity of the molecule. The second concept is electronegativity, specifically as it applies to dipole moments in bonds. So electronegativity is the affinity of electrons that a particular atom has, and it increases as you go across the periodic table and up the periodic table. So fluorine is the most electronegative atom on the periodic table of all of the elements. And so when we look at a bond for an organic molecule, you generally are going to have a carbon and then something else attached to it. So if that something is a heteroatom, we want to be able to understand how those electrons are shared. From looking at a Lewis structure, it appears that those electrons are shared evenly, but really they're not. We know that the fluorine has a higher affinity for electrons. It's more electronegative, and so it has a partial negative charge, and the carbon has a partial positive charge. So those electrons are more towards the fluorine than they are the carbon atom. Carbon is going to be the least electronegative atom in most organic molecules unless there's a metal attached to the carbon. And so again, we can look at double bonds like the carbon-oxygen double bond, which is commonly found in organic molecules. And again, the carbon has a partial positive end, the oxygen is partial negative. And so using this dipole moment and these partial charges, we can again predict reactivity for that molecule. The third concept is going to start to tie the first two together, and that is that in chemistry, opposites attract. So if we can assign charges, if we can understand polar bonds, then we can understand what two atoms are going to be attracted to one another and how a chemical reaction might proceed. So looking at the system I have laid out here, I have two organic molecules, so they're methyl-based. We have a CH3 on each of them. On the left-hand side, I have a sulfur, and this sulfur is right under oxygen in the periodic table, so it behaves the same way often. So again, here's our sort of mini periodic table. So sulfur is also neutral when it has two bonds and two lone pairs of electrons. You can see here that it has 3 lone pairs of electrons, and it's going to be negatively charged. Now, when we look at our other molecule, there is nothing charged on there. Halogens are terminal atoms. They have 3 lone pairs of electrons and a single bond, generally speaking. But chlorine is more electronegative than carbon. So there's going to be electron density pulled towards the chlorine atom, away from the carbon atom, such that the carbon is partial positive and the chlorine is partial negative. So now that we know our charges and our partial charges, we can understand that this sulfur that is negatively charged is going to be attracted to this carbon that is partially positively charged when those two molecules are in close proximity to one another. Okay, so we know how to assign a formal charge, we know how to predict a dipole moment, and we know that opposites attract. So the next step, and this is about 3/4 of an organic chemistry class, is mechanisms, arrow pushing. How does a reaction proceed? Okay, so what bonds are broken? What bonds are formed? How do electrons move? We use arrows to show that progression. For a more in-depth look at how to correctly use arrows, I have a video for you. It's queued up at the end of this, or you can just look on my channel. But we're going to do our first example here. So we discussed previously that the sulfur is negatively charged, and it will be attracted to the partially positively charged carbon over here. So my arrow is going to begin at one of these lone pairs of electrons on the sulfur atom, and it's going to end at the partially positively charged carbon. That arrow indicates the formation of a new bond between sulfur and carbon. The carbon-chlorine bond is breaking, so my arrow begins at the bond between those two, and it ends on the chlorine atom because the chlorine is accepting those electrons. It's negatively charged over there. So if we wanted to label this first arrow 1 and this second arrow 2, the formation of this bond here would be explained by arrow 1, and the formation of the chloride ion and that extra lone pair of electrons would be explained by arrow 2. Okay, so understanding how arrows work, how to draw them correctly to communicate how a reaction is proceeding is vital to success in organic chemistry. Okay, and the last piece of advice I have for you is don't memorize. There is way too much material in organic chemistry to memorize. There's just no way to do it well. So you need to understand why things are happening. I've told you 4 fundamental concepts prior to this step that are going to repeat themselves over and over and over again in organic chemistry. If you can master those skills, you can apply them to different situations. If you try to memorize a specific problem, something on it is going to change in the next iteration and you won't know how to do it anymore. Do different problems. Don't go over your notes again. Don't do a problem set that you have already done. Don't work on homework problems that you've already completed. The more different ways you solve a problem, the better prepared you're going to be for that challenging problem on the exam. Okay, that's passive studying. You want to do active studying. You want to try doing different iterations of something that's giving you trouble. And lastly, get help. Go see your professor, see a tutor, come see me at Chemistry with Caroline. People want to help you, okay? And it is way more time efficient to just go get the help, talk to an expert, or seek a resource so that you can be successful and your time studying will be better spent. So if you found this video helpful, please like, subscribe, and share with your friends, and I'll see you next time.